Hello everyone. Welcome to the another lecture of periodic classification of the element class 11. Myself Suman Singh. So in the last class we have discussed about the valencies. So now in this class we will discuss about ionization energy or ionization enthalpy. Okay. So when we talk about the ionization energy or ionization enthalpy, what we can say, as we know that an atom is what it is composed of a positively charged nucleus, right, and the negatively charged electrons revolving around it, right. This is the basic concept of atom. Now this nucleus, what it is doing, this nucleus is exerting, or we can say that this nucleus exert an appreciable force of attraction, right, on that planetary electrons. So what we can say, if you want to remove an electron from an atom, okay, we will have to, what we have to do, we will have to supply an energy to overcome the force of attraction exerted by the nucleus on the electron, right. So this energy which is required to overcome the force of attraction exerted by the nucleus on an electron, this energy is called what? Ionization enthalpy or ionization energy. Okay, let me tell you one thing. Suppose this is our nucleus and this is our first cell, this is the second cell, like this. Suppose here is an electron. So this, as we know that this nucleus, suppose this is the nucleus here, this is positively charged nucleus. So what it will do, this nucleus will exert some force to this electron, right. So suppose the force which is exerted by this nucleus is, suppose we can say that 20 joule. Okay, so 20 joule. So what we have to do, if you want to remove this, if you want to remove this electron from here, so what we have to do, we have to supply extra energy, right. We have to supply extra energy which will be more than 20 joule. Suppose it may have to, we may supply 22 joule or 30 joule, like this, then only it will come out, right. This, and this electron will come out from here. So this extra energy which we are supplying to remove an electron from an isolated gaseous atom, this is called what? Ionization enthalpy. Okay, I hope you have understood this. So now we will see detail about the ionization enthalpy. So this energy is called what? Energy, ionization enthalpy or ionization energy. Okay, so if we want to define this ionization energy or ionization enthalpy, what, how we can define, we can define like this: the amount of energy, okay, which is required to remove the most loosely bounded electrons from an isolated gaseous atom, okay, to form a gaseous ion, is called what? Ionization enthalpy or ionization energy of an atom. Okay, so how we can write, we can write like this. Suppose we have this, okay, and gaseous atom, and from this gaseous atom we are supplying here energy. Okay, energy, and that energy may be, then may be written as IE, ionization enthalpy, or it may be written as del IH. Okay, so what it will give, it will give M plus here, and electron will come out, right. So this energy is called what? Ionization enthalpy. Okay, so its unit, when we talk about its unit will be kilojoule per mole. Okay, its unit will be this. Now one more word is there related to this ionization enthalpy, which is ionization potential. Okay, so what is this ionization potential? So when we talk about the ionization potential, ionization enthalpy or ionization energy can be measured in a discharge tube. Okay, so if we want to measure this, we can measure this measured in a discharge tube containing the gas under containing the gas under a low, under a study at low pressure. Okay, what we can say, the ionization energy or ionization enthalpy can be measured in a discharge tube containing the gas under study at low pressure. Okay, now at a certain voltage between the cathode and an anode, okay, at a certain voltage between the cathode and the anode, the gas get ionized, right. Now the ionization of gas is what? It is indicated by the sudden large increase in the flow of current, okay, through the gas. So the voltage at which the ionization of gas occur is known as what? Ionization potential. Okay, and is numerically equal to the ionization energy of the gas under study in electron volt. Okay, it is studied under electron volt. So what we can say, the ionization potential um, is very often expressed in the electron volt. Okay, about electron volt we have discussed in the atomic structure, right? So it is often expressed in electron volt and is used to convey the sense of ionization energy. So what we can write, we can write like this: 1 electron volt, which is equal to 1.6021 into 10 to the power minus 19 joule. Okay, or we can write like this: 1.6021 into 10 to the power minus 22 kilojoule. We can express this electron volt like this. So this was about the ionization potential. Okay, so now we will see the factors on which this ionization energy depends. Okay, so when we talk about the factors on which this ionization energy will depend, so first of all, first will be the size of atom. Number one will be size of atom. Okay, number one will be size of atom. Okay, so when we talk about the size of atom, so the ionization energy of an atom is governed by its size. Okay, size, that is what it is talking about, atomic radius. Okay, atomic radius, right? So in a large atom, when we talk about the large atom, the valence electron is are far from the nucleus, right? As we can say, if we are talking about the large atom, suppose like this, the electron will be very far away from the nucleus. Suppose here is electron, so you can say it, right? It is very far away from the nucleus, right? So in the large atom, the electron are far from the nucleus. Okay, and experience a less force of attraction as compared to the smaller atom, in which the valence electrons are near to the nucleus. Okay, and the experience of greater force of attraction, as you can see, I will give you one example here. Suppose we have one example is this. Okay, one example is this, and another example is this. Okay, this one, suppose here it is one electron is here, and when we talk about this, here it's one electron. So this one is larger, right? This one is large. Okay, and this one is small atom. Okay, so in the large atom, the valence electron are far away from the nucleus. As you can see, it is very far away from the nucleus, right? And and if it is far away from the nucleus, it will experience a lesser force of attraction as compared to the smaller one, as compared to this, right? As compared to the smaller atom, in which the valence electron is near to the, as you can see, the valence electron is very near to the nucleus, right? The valence electron is very near to the nucleus, and it will experience a greater force of attraction, right? This one will experience a greater force of attraction as compared to this, right? So the attraction force between the electrons and the nucleus is what? It is inversely proportional to the distance between them, right? The attraction force between the electrons, so what we can say, the attraction force between the electrons and the nucleus is inversely proportional to the distance between them. So what we can say, as we can say that further away the electron from the nucleus, lesser will be the force of attraction on it, and more easily it can be removed, right? If it is very far away from the nucleus, if the electron is very far away from the nucleus, it will be very easy to remove this, right? Because there will be a less force of attraction between this electron and the nucleus, right? So what we can say, consequently, further away the electrons from the nucleus, less would be the force of attraction on it, and more easily we can remove it, right? So what we can say at last, what we can say, the ionization energy decreases with the increase in atomic size, right? As you can see, if the atomic size is increasing, we are just using less amount of ionization energy, right? We will the ionization energy will decrease. If we will supply very less amount of ionization energy, then we can easily remove the electron. So what we can say, the ionization energy decreases with the increase in atomic size. Okay. Now next factor is nuclear charge. Next factor, factor number 2 is nuclear charge. Nuclear charge. Okay. Now, next one is nuclear charge. So, when we talk about the nuclear charge, what we can say, with the increase in the magnitude of the nuclear charge, if the magnitude of the nuclear charge is increasing, the valence shell electron will experience a greater pull towards the nucleus, right? If the magnitude of this nuclear charge, suppose the magnitude of this nuclear charge, if it is increasing, then what will happen, the valence shell, this one is valence shell, right? This one is valence shell. So this valence shell will experience more and more, what it will experience more and more um, pull towards the nucleus, right? If the magnitude of the nuclear charge is increasing. So what we can say, it will now what will happen if the magnitude of the nuclear charge is increasing, then the nucleus will exert a greater force to pull the electron towards itself. So at that time what will happen, it will become more and more difficult to remove the valence electron, okay, or it will become difficult to remove the valence shell electron, right? So what we can say, the ionization energy, okay, the ionization energy increases with the increase in nuclear charge, provided the valence shell remain the same, right? So what we can say, if with the increase in the magnitude of the nuclear charge, the valence shell electron experience a greater and greater pull by the nucleus, right? So therefore it will become more and more difficult to remove the valence electron, okay, or we can say the valence shell electron. So at last what we can say, the ionization energy increases with the increase in nuclear charge, okay, provided the valence shell should be same, okay. So this was about the nuclear charge. Now we will talk next is screening effect, okay. About screening effect I have also discussed, right, in the previous lecture. If you will see, we have discussed about the screening effect, right? Screening effect, or it is also called shielding effect, okay. So when we talk about the screening effect or shielding effect, let me tell you like this. So in the multi-electron atom, if there is a multi-electron atom, the electron present between the nucleus and the valence shell, what it will do, it will shield the valence electron from the nucleus. Let me draw here, right, so that you can understand carefully, very clearly. So as you can see, suppose this is an atom, okay. So in this atom, suppose here is one electron, and here is suppose 1 2 3 4 5 6 7 8, here also 1 2 3 4 5 6 7 8, and here 2, suppose 1 2, like this is there. So what will happen, this is a multi-electron structure, right, multi-electron atom. So the electron present between the nucleus and the valence electron, as you can see, this is the valence electron, right? This one is what, this one is valence electron here, and this one is our nucleus. As you can see, this one is our nucleus, and the valence electron is this, right? So what will happen, the electron which is present between him and between this and this, whatever the electron is present, as you can see, between this and this, between this and this electron and this nucleus, so many electrons are present, right? Like this 1 2 3 4, so many electrons are present, as you can see. So what it will do, this will shield the inner electron. This is called what? Inner electron. So the electron present between the nucleus and the valence shell, okay, this will shield the valence electron from the nucleus, okay. Or what we can say, this will decrease the effect of nucleus on the valence electron. Means what? It these electrons which is present between this valence electron and the nucleus, these electrons will, what it will do, it will decrease the effect of nucleus on the valence electron, okay. Due to the presence of inner electron, what will happen? Due to the presence of this inner electron, the nucleus will exert a less force of attraction on the valence electron, right? Because the whatever the force which will be exerted by this nucleus, with this nucleus, this force will be shielded by this electron which is present between them, right? So what will happen? The nucleus will exert a less force on this electron, right, on this valence electron. What we can say, the nucleus will exert a less force of attraction on this valence electron, okay. So this effect, okay, this effect is called what? Screening effect or shielding effect, okay. And a decrease in nuclear charge felt by the valence electron, and due to this, what will happen? There will be a decrease in nuclear charge felt by the valence electron. Now the how we can define this? If you want to clearly define this, what we can say, the actual charge felt on the valence electron is known as what? Effective nuclear charge, okay. Suppose the actual charge, which if these electrons are not there, suppose, okay, these electrons are not there, at that time, but the charge which will be felt by this electron, okay, at that time the charge which will be felt by this electron is called what? Effective nuclear charge, okay. And that is denoted by Z, okay, that is denoted by Z star, like this, okay, Z star, okay. So if you want to define this effective nuclear charge, what we can write? The effective nuclear charge, this one, will be equal to, well, let me write here, I am erasing this one, okay. So suppose the effective nuclear charge, which was the actual charge which was felt by the electron, okay, that's called what? Effective nuclear charge, and it is denoted by this, right? This, right? So if you want to define this, what we can write? Effective nuclear charge will be equal to Z minus S. So now here, what is Z? Z is what? This Z, where this Z is the actual nuclear charge, okay. And S is what? The S is a constant known as screening constant, or known as shielding constant, okay. I hope you have understood this, right? Now, so the screening effect, what we can say, the screening effect depend upon the number of inner electron, okay. If the number of electron, inner electron is greater, the shielding effect will increase, and consequently what will happen? The effect of nuclear charge on the valence electron will decrease, okay. So what we can say, greater the number of inner electrons, okay, greater would be the screening effect, and consequently less would be the effective nuclear charge experienced by the valence electron, right? So what we can say, in if other factor remain the same, if other factors is not affecting that atom, or if the atom, then what we can say, the ionization energy decreases with the increase in the number of inner electron, right? I hope you have understood this, right? Now next, penetration effect of an electron. So what is the penetration effect? So when we talk about the penetration effect, now when we talk about the penetration effect, what we can say, in a multi-electron, okay, in a multi-electron atom, the electron cloud of various electron do not maintain a distinct boundary. I hope you are understanding what I mean to say, right? In a multi-electron atom, what will happen? The electron cloud of various electron do not maintain a distant boundary, okay. So what will happen? Instead, the electron cloud of one electron penetrate into the electron cloud of some other inner electron, okay. So at that time, what will happen? The effect, that effect is known as penetration effect. Means what? The electron cloud of one electron penetrates into the electron cloud of some other inner electrons. Okay, this effect is called what? Penetration effect. Okay, and now due to this effect, number 4, let me write here, penetration effect. Okay, Penetration, penetration effect. Penetration effect. So now due to this effect, I hope you have understood what is penetration effect. Now due to this effect, what will happen? The electron shift towards the nucleus. Okay, and experience a greater pull by it. Due to this penetration effect, what will happen? The electron will shift towards the nucleus and it will experience a greater pull by it. Okay, so after that, what we can say, for a given value of n, suppose for a given value of n, which is a principal quantum number, right, the probability of finding an electron near the nucleus decreases as the value of L increases, right, as L is what? Azimuthal quantum number, right. So if the value of L will increase, the probability of finding an electron near to the nucleus will decrease, right. I hope you have learned this in atomic structure. Now since the value of L decide the nature of the subcell, so what we can say, the probability of finding an electron near the nucleus will follow some order, right, like this order. It will follow some order like this, as after that P, after that D, and after that F. Okay, so what we can say, this means what is the meaning of this? This means that S electron can penetrate better than a P electron, which in turn penetrates better than a D electrons, and F possess a least tendency to penetrate. Okay, I hope you have understood this. Now with the penetration power of an electron, if the when the what we can say, like, we can say like this, if when the penetration power of the electron is more, at that time what will happen? It will be closer to the nucleus. Okay, and more energy will be required to remove it. Okay, I hope you have understood this, right. So what we can say, for the same value of n, right, for the same value of n, the ionization energy of S electron is greater, okay, than that of the P electron, which in turn is greater than the D electron, and so on, right. So what we, at last what we can say, for the same shell, the ionization energy follow the order which is this. Okay, so I hope you have understood this, right. So now the next factor is electronic configuration, which is the last factor. Okay, after that we will see the uh, after that we will see variations. Okay, the last factor is electronic configuration. Okay, so when we talk about the electronic configuration, so we can say like this, the electronic configuration of atom may also affect the value of ionization energy. Okay, so always remember that the half filled and completely filled shell are found to be possess extra stability. Okay, whenever there is a half filled, suppose like this, whenever there is a, if it is like this, right, so this is what, this is half filled, right, and this is completely filled, right. When we talk about the p orbital, suppose this is a p orbital, right, p, so this is half filled and this is what, completely filled, right. So always remember that the half filled and completely filled are found to possess extra stability. Okay, and the atom having a completely filled subshell. Okay, and the atom having completely filled subshell, just like this, just like this. Okay, wait, let me draw it nicely, just like this, like this. Okay, so the atom having completely filled subshell are said to possess stable electronic configuration. This one we know, right. So the atom having a filled shell also show an extra stability. Okay, so what we can say, this type Okay, we can say like this type and this type of filling of electron will be more stable. Okay, and this one will be more stable, after that this, after that this. Okay, so now next is what, then such atoms possesses less tendency to lose electron. As now we can easily understand, right? If it is completely filled or half filled, then it will possess it will have a less tendency to lose the valence electron, and consequently what will happen, the ionization energy will increase, right? So what we can say, if we are talking, if we are asked to take an example, so as we know that, right, helium, when we talk about the helium, so helium has an electronic configuration of 1s2, right? So 1s2 means what, the k shell is completely filled. Okay, so that is why the ionization energy of helium is much greater than that of the hydrogen. Okay, and other noble gases, if you take the other noble gases, which so you will generally see the electronic configuration will be ns2 and np6, right, np6. So other gases also possess completely filled shell with a suitable with a stable configuration, which is this np ns2 and np6. So what we can say, the all the noble gases, okay, have a very high ionization energy. Okay, because its electron, because its shells are completely filled, as you can see, right? Now again, if you're talking about if you are taking the example of this beryllium and magnesium, etc., so at that time it will possess electronic configuration of type like this, right, ns2, right? So in which the s orbit is completely filled, as we know, when we see the electronic configuration of beryllium, s orbit is completely filled, right? So therefore what we can say, these electrons have a high ionization energy. Okay, because its s electron are completely filled. Okay, now next is elements like nitrogen, phosphorus, okay, etc. It will have an electronic configuration like this, right, ns2 np1x np1z npz1, right, like this electronic configuration is there, right? So in this configuration, p orbital belongs to the valence shell. Okay, and exactly half filled, as you can see, exactly half filled, right, exactly half filled. So what we can say, these elements show a higher stability and hence relatively what, higher ionization energy. Okay, so I hope you have understood this, right? Now next we will see variations. So when we talk about the variation of variation across the period, okay, ionization enthalpy, variation of ionization enthalpy across the period. So always remember that in general, when we talk about in general, the ionization energy increases with the increase in atomic number across the period. Okay, means what, it will increase, it will increase across the period, it will increase, right? Now next is the gradual increase in the value of ionization enthalpy on moving from left to right in the period is due to the combine effect. Okay, it is not the only one factor will determine, because of only one factor, there is a gradual increase in the ionization enthalpy on moving from left to right. Okay, that is not only the one factor. Okay, there are some multiple factors which because of that, there is a gradual increase in the value of ionization energy. Okay, so what was that factor, we will see. The first factor is the nuclear charge. Okay, since the nuclear charge is gradually increasing, okay, the nuclear charge increasing regularly with the increase in atomic number, because we know that when we go across the period, the atomic number will increase, right? Since the atomic number is increasing, so because of that, the nuclear charge will also increase. This is the first factor, because for the gradual increase. Okay, now next factor is number of cells remain the same. Okay, when you will see the period, across the period, number of cells will remain same, right? Number of cells will not decrease, it will be same. Okay, or it will not decrease or increase, it will remain same. Okay, so since the number of cell remain the same and the differentiating electron enter into the same cell. Okay, so that is why also there is a gradual increase in the ionization energy. Okay, now next is size of the atom decreases because there is an increase in the nuclear charge, and because of the increase in nuclear charge, we have discussed about this, right? Because of the increase in the nuclear charge, the electron will pull, and the valence electron will be pulled towards the nucleus more likely, right, more strongly. That is why the size of the electron increases, the size of the atom decreases, right? Now, due to these three factors, or due to this combined effect of the combined effect, the effective the attractive force between the nucleus and the valence shell increases on moving from left to right in the period. Okay, I hope you have understood this, right? So what we can say, more and more energy is required to remove electron from the atom, and consequently the ionization energy increases with the increase in atomic number in the period. Okay, so I hope you have understood this now. So here there are certain exceptions also, right? We have to see the exceptions also. It is not likely that it is following the regular trend. There are some exception. We will see that. What was that exception? The exception is between boron and oxygen. Okay. So when we talk about, we will take the example. Okay. We have boron and oxygen. Okay. Boron and oxygen have a lower ionization energy as compared to beryllium and nitrogen. Okay. How we will see this, right? So when we talk about, it is given, suppose here, I think, no, it is not given here, I will write here. So suppose we have here beryllium. Okay, so beryllium, when we talk, its atomic number is 4, right? So when we see its electronic configuration, it will be 1s2, okay, and 2s2, right? And boron will be 5, so it will be 1s2, 2s2, and 2p1, right? So what we can say, boron possesses an higher nuclear charge, right? Yet its ionization energy is less, okay, as compared to that of the beryllium. Okay, when you will see the trend in the ionization enthalpy, you will see that the boron, okay, when you see the trend in ionization energy, it is seen that boron possesses an higher nuclear charge. Okay, boron has higher nuclear charge. Okay, but it yet, what we can say, yet its ionization energy is less as compared to that of beryllium. Why it is happening, we will see this. As you can see, the first factor is here 2s. Okay, the 2s electron are more penetrating than 2p electron, right? As we have discussed previously, penetration effect, right? Now next is 2s electron in beryllium, right? This 2s electron in beryllium is not shielded by the inner electron as efficiently as 2p electrons in the boron. As you can see here, this one is only shielding, right? But here, if we, in this case, these two are shielding, it is showing a shielding effect. That is why this is the another factor why the boron has a less energy and less ionization energy. Okay, now third factor is beryllium possesses a stable electronic configuration. As you can see, is s orbital is completely filled, right? So what we can say, this beryllium possesses stable electronic configuration as all the orbits are completely filled in it, right? Now due to this factor, whatever the three factors I have told you, these three factors, because of these three factors, beryllium possesses much higher ionization energy, okay, as compared to the value it should have otherwise. Okay, so at last what we can say, the value of ionization energy of boron in accordance to the regular trend, but due to the sudden increase in the value of beryllium, the ionization energy of boron appears to be low. I hope you have understood this, right? Now again, next similarity is nitrogen and oxygen. So nitrogen, we will see this here, it is 1s2, 2s2, after that 2px1, 2py1 here, and 2pz1 here, like this, right? And for oxygen, when you will see, it will be 1s2, 2s2, 2px2, and 2py1 and 2pz1, right, like this. Now similarly, what we can say, a decrease in the ionization energy is going from nitrogen to oxygen, okay, due to the presence of half filled cell in nitrogen, due to the presence of half filled cell in the nitrogen, as you can see here, okay, which make its electronic configuration relatively more stable. As you can see, as I previously I have told you, right, if it is a half filled, completely filled, it is more stable, right? So that is why it makes nitrogen, its electronic configuration relatively more stable, and give a boost to the ionization energy of the nitrogen, okay. And due to the higher ionization energy of nitrogen, ionization energy of oxygen appears to be get lowered, okay. And exceptionally, what we can say, exceptionally very high value of ionization energy of neon is due to the stable electronic configuration. When we talk about the neon, so there will be exceptionally very high ionization energy of neon due to the stable electronic configuration, okay. So I hope you have understood about the exception of beryllium and boron and nitrogen and oxygen, right? Now we will see the variation in period group, okay. So when we talk about the variation in group, we can say general like this: the value of ionization energy decreases regularly with the increase in atomic number on going down the group. So there are some factors because of which there is a regular decrease in going down the group, okay. And that factors are: number one, first factor is what, the number of cell, and therefore the size of the atom is increasing with the increase in atomic number in going down the group. This is the first factor because of which the value of ionization energy decreases regularly with increase in atomic number on going down the group, right? So number one is number of cells and the size of atom increasing, okay. Now number two is due to the increase in the number of inner electron, the shielding effect increases. As I have told you, in more and more number of electron in the inner shell, then the more will be the shielding effect. So due to the increase in the number of inner electron, the shielding effect increases, okay. And the value and the valence electron gets more and more loosely bounded to the nucleus as the atomic number increases in going down the group, right? So these are the two factors uh, which which affects the value of ionization energy. Now what we can say, although the nuclear charge increases in going down the group, the effect of increased nuclear charge, okay, because as you can see, when we are going down the group, the nuclear charge is increasing because the atomic number is increasing. That is why the nuclear charge is increasing. But the effect of this nuclear charge, it will be get cancelled by the by an increase in the atomic size, okay, and increase in the shielding effect. Due to the shielding effect and atomic size, the effect of this nuclear charge will get cancelled, okay. And what we can say, the attractive force between the nucleus and the valence electron go on decreasing with the increase in atomic number, okay. So at last, what we can say, finally, the ionization energy of the elements decreases regularly in going down the group, okay. So I hope you have understood what is ionization enthalpy. So it is very important topic for your exam. So so in the next class we will discuss about the electron affinity and electron negativity, okay. Till that, thank you.